In this video, we're going to look at some of the reactions of carboxylic acids. Acid-base reactions are probably one of the most important types of reactions that carboxylic acids will undergo, but this is discussed separately. We're going to take a look at esterification, reduction, alkylation, and conversion to acid chlorides. Carboxylic acids can undergo Fischer esterification by treatment with an alcohol in the presence of H+, giving us the ester with water as a byproduct. Notice this is an equilibrium reaction. So in the forward direction, this is esterification. In the reverse direction, this is ester hydrolysis. If your goal is to make the ester, then you might use an excess of acid or an excess of alcohol to take advantage of Le Chatelier's principle and shift the equilibrium to the right. If both of your starting materials are expensive or if they would be difficult to separate, another approach would be to remove water, which would pull the equilibrium to the right as well. If your goal is to hydrolyze the ester, then you would use a large excess of water to push the equilibrium to the left. As an example, we can take a look at the esterification of isopentyl alcohol with acetic acid in the presence of sulfuric acid to give isopentyl acetate. Let's consider the mechanism of this reaction. I'm going to stick with acetic acid, but I will use a generic alcohol. So acetic acid can grab off a proton from sulfuric acid to give the protonated carboxylic acid. Now the alcohol can act as a nucleophile and share its electrons with this carbon, pushing these electrons onto the oxygen, which would give us this. And then another molecule of alcohol can act as a base, grab off this proton, put these electrons back onto the oxygen, and that gives us the OH, OH, and OR. I'm going to rewrite that over here. Now this intermediate can grab off a proton from sulfuric acid, but the question is where? Well, if this oxygen grabs a proton, well, we're just talking about going backwards. And so this is an equilibrium that is going to happen. So let's instead think about what happens if one of these OHs grabs the proton. It doesn't matter which is which. So let's say this is the one. So we have this, and here is the OR. Let's include these lone pairs. Next, water can leave. We can think about this oxygen helping out. So these electrons can come in here to form a double bond, helping to push away water as a leaving group. Giving us this. And then finally, another molecule of the alcohol can act as a base, grab off this proton, put these electrons back onto the oxygen. I'm going to have to write this down below, giving us our ester product. So notice what we have is kind of two stages. Here we have the formation of this tetrahedral intermediate, and then the second stage would be the dissociation of the tetrahedral intermediate. What we're looking at is the overall mechanism for nucleophilic acyl substitution. There was a lot of controversy about the mechanism of nucleophilic acyl substitution and esterification and ester hydrolysis in particular. Notice in this example, I went with color coding, where the part that came from the alcohol is red, what came from the acid is blue. I left the oxygen different because, well, does this come from the alcohol or is it from the carboxylic acid? Well, in 1938, Roberts and Urey carried out an experiment using acetic acid with methanol, but the methanol had oxygen labeled as O18. This was treated with sulfuric acid to make methyl acetate with water as a byproduct. Now they isolated the products and looked for the presence of the oxygen 18 label. If we consider, so this is our labeled oxygen, what they found is that that oxygen here was labeled. So this was the O18. Now, are these experimental results consistent with this proposed mechanism? Let's think about, this is our alcohol, and let's have it labeled. Let's use the green as signifying the label. So when this adds here, this is the labeled oxygen. In other cases where the alcohol is just grabbing off a proton, well, that doesn't really matter. We still have this oxygen is labeled. This is the labeled oxygen. This is the labeled oxygen. This is the labeled oxygen. And in our final product, this is the labeled oxygen. And so, yes, this mechanism is consistent with these experimental results. Keep in mind, a mechanism can never be proven, but additional experimental evidence can be collected which supports a particular proposed mechanism. In the nearly 100 years since this experiment was carried out, there has been a lot of other experimental evidence supporting the idea that general nucleophilic acyl substitution proceeds by the formation and then dissociation of a tetrahedral intermediate. Carboxylic acids can undergo reduction. First, let's consider the reduction to alcohols. If we have a carboxylic acid, this can be treated with lithium aluminum hydride, followed by aqueous workup to give a primary alcohol. So what's happening here? Lithium aluminum hydride can act as a base and grab off this proton, which will give us some of the carboxylate, where this would be associated with lithium. We will also form some hydrogen as well as some aluminum trihydride. Now this can also act as a source of hydride. So one of these hydrides can act as a nucleophile, share its electrons with this carbon, pushing these electrons up onto the oxygen, giving us this, where one of these oxygens is associated with lithium and the other would be associated with aluminum. And I forgot the hydrogen that just added. Next, one of these lone pairs can come back in here to reform the double bond, pushing away this oxygen to run off with the aluminum. And that gives us an aldehyde. But we still have lithium aluminum hydride present. So another hydride can act as a nucleophile, sharing its electrons with the carbonyl carbon, pushing these electrons up here, giving us this, where we now have two hydrogens connected to what used to be our carboxylic acid carbon. And then finally, when this undergoes aqueous workup, this O- can grab a proton, resulting in the formation of our final product. Notice all of our carbons were in the starting material, and this oxygen was one of the carboxylic acid oxygens. The two hydrogens that became connected to what was the carboxylic acid carbon, those both came from the lithium aluminum hydride, and then the hydrogen on the alcohol, that came from the aqueous workup. So this is how a carboxylic acid can be reduced to an alcohol. What about reduction to an aldehyde? Well, there really aren't very good methods to do this directly. So a few approaches can be taken. One is that the carboxylic acid can be converted to the acid chloride by treatment with thionyl chloride, for example, and then the acid chloride can be reduced by this reagent, for example, lithium tri-T-butoxy aluminum hydride, and that would give the aldehyde. Another option is that a carboxylic acid could be converted to an ester, and then the ester could be reduced to the aldehyde using something like Dibol. And yet another approach would be to reduce the carboxylic acid all the way down to the alcohol and then oxidize it back up to the aldehyde. So while we're not going to talk about any ideal methods to convert a carboxylic acid directly to an aldehyde, we have seen two-step approaches that would allow this overall transformation. Carboxylic acids can also undergo alkylation using organolithium reagents. You could take a carboxylic acid and treat it with two equivalents of an organolithium, and that will give you a ketone where you maintain this part of the carboxylic acid, but you have added now this alkyl group that came from the organolithium. For example, if we take benzoic acid and we treat it with two equivalents of ethyl lithium, we will be able to isolate this ketone. So what's going on? The first equivalent of ethyl lithium can act as a base and grab off the carboxylic acid proton, giving us this carboxylate. Next, a second equivalent of ethyl lithium can now act as a nucleophile, pushing these electrons up here, giving us this. Now, when water is added as part of the workup, both of these oxygens are going to be protonated. While this happens, any remaining ethyl lithium will also be quenched. So there's no more organolithium present. A single carbon is connected to two OH groups. This is a hydrate. So in the reverse of hydrate formation, this hydrate can be converted to this ketone. And also note, by the time we have the ketone, all of the organolithium has already been quenched. And so you're not going to have addition of the organolithium reagent to the ketone, and so you'll be able to isolate the ketone. Carboxylic acids can be used to prepare acid chlorides. For the conversion of carboxylic acids to acid chlorides, your carboxylic acid could be treated with thionyl chloride or oxalyl chloride to give the acid chloride. Here we have a couple of examples. If we have oleic acid, this carboxylic acid will be treated with thionyl chloride, converting it to the acid chloride, and this worked very well. And the byproducts are SO2 and HCl, both given off as gases. And another example, here we have 3-phenylpropanoic acid. This is treated with oxalyl chloride to give the acid chloride, again in very good yield. And these are the byproducts, which again are all given off as gases. Once we have formed acid chlorides, these can be converted to ketones or to aldehydes, or they can be used in nucleophilic acyl substitution to be converted to esters and amides, thioesters. So a number of different transformations are possible using acid chlorides.